All right, I will begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you bless this class, Lord, and just help us use this time wisely, Lord. In your name I pray. Amen. All right, so today, of course, is lecture 3. And I have the privilege of sharing with you today one of the central ideas of this course, which is isomorphism. So, in particular, we're going to talk about isomorphism of groups. So we say two groups are isomorphic if they're essentially the same group, and they have the same structure in some sense, and maybe we're just using a different notation, but at its core, it's the same object. This is kind of the intuitive idea. But we don't work on intuition in here, we work on definition. So here's the definition for you of isomorphism. So let G1 and G2 be groups with operation 1 and operation 2. So I'll use star sub 1 for the first group and star sub 2 for the second group operations. All right. Then psi from G1 to G2 is an isomorphism, all right, if psi is a bijection. What's that mean when we say something's a bijection? It's injective and surjective. It's one-to-one and onto, right? So if it's a bijection, and it preserves the structure in the following sense. Psi of x times 1, y, is equal to psi of x times 2, psi of y. I'll add some parentheses in here just to make sure that there's no confusion. I'm saying that the multiplication in the domain, so this is a multiplication in G1, right? And on the other hand, over here on the right-hand side, we're talking about a multiplication in G2, right? So in this sense, the group operation is preserved by this bijection, all right? And that has to be true for all x and y in G1. If such an isomorphism exists, then we say G1 and G2 are isomorphic, and write G1 equals with a squiggle over it, G2. They're congruent in that. Well, it's not congruence, it's isomorphism, but it turns out isomorphism of groups is also an equivalence relation. So this is the definition. I've pointed out some examples of this already. Let me give you an example here. I'll start out small. If you, I believe this example is relevant to the license plates that Dr. Sprano has in his office. Let's see here. 0101 Z2, 0110. This is U3, which we defined last time, the group of units, mod 3, right? So I'm writing the Cayley tables here. Here's U4. Oops. I try not to, I'm not putting those dividers in at the moment. Let's see here, 1, 3. So 1, 3, 3, 1. So these are 3 groups. Each one of them has order too. By the way, for a finite group, you guys know a little bit about set theory already, right? Two sets have the same cardinality if what? If there exists a bijection between them, right? So in the case of finite sets, if you've got a bijection between finite sets, you already know from just study of set theory that they have to have the same number of things, right? So there's hope that these three groups are isomorphic because at least they have the same number of things. Even without the condition here on the multiplication, the assumption that it's a bijection already tells you that the cardinality of isomorphic groups has to be the same. So there's hope that these three groups are isomorphic. And in fact, you can show that if you set psi of 0 equal to what and psi of 1 equal to what? What should 0 map to keep the pattern the same? 0 should map to 1. 1 should map to what? 2. That would define an isomorphism from Z2 to U3. If you wanted to define an isomorphism from U3 to U4, let me use phi as a map. We'd set phi of 1 equal to what? And phi of 2 equal to what? Uh-huh. Right. Now, if you want me to be fussy, and I don't know, some of you probably do, what would we write here if we were going to be careful about the notation? So this would be like 0 sub 2 maps to what? 1 sub what? 3, right? And to give you a flash, here, this would say phi of 2 mod 3 maps to what? 3 mod 4, so. But what I wrote in red doesn't have to be written. It should be understood from the context here that we're talking about a different copy of 1 in the different context, right? So those are isomorphisms. You can check all the cases. But let's make an agreement that if we're talking about groups of small order, if you can write the Cayley table for both and make a convincing argument that they have the same pattern, that suffices to prove that those groups of small order are isomorphic. It's just checking cases after that point. If they have the same pattern, that means that when you multiply elements, they multiply in the same way, which is to say that the structure preserving rule is holding for all the pairs. This is an important comment because I accidentally assigned the isomorphism of something like a group of order 8 last year or the year before, and I hadn't made this comment, and so you're obligated to write this like case-wise defined function with 8 cases and then sort through how all the different products no. Much better for a group of small order to simply write the Cayley tables and say, you know what, that's the same pattern, so the multiplication transfers. Now that, of course, that method of proof won't work for us in my second example. My second example is not a finite example. This is an infinite example. We're going to look at f going from the real numbers to the set of positive real numbers. So here we're thinking about G1 as the reals with addition, and we're thinking about G2 as being 0 to infinity with multiplication, right? So what do you think, what's the mapping going to be? F of x equals to what? What would give us, what I'm arguing for you guys is, in fact, these groups are isomorphic. So we want addition in the domain to transfer to multiplication in the range for our isomorphism. What should we write down here? You're like, I read the notes because I realized I'm a responsible student, reads the notes ahead of time, so I refuse to answer this question because I'd just be saying back to you what you already told me, right? That's the reason none of you are telling me it. Yes. Very good. So e to the x. E to the x will work nicely. I mean, you could play around with different things, but check it out. Does that work? Well, what is f of x plus y? That's e to the x plus y, which we know is e to the x times e to the y, which is f of x times f of y. So it's structure preserving. It transfers addition to multiplication like we want. Is it a bijection? How do you prove something's a bijection? Well, there's a lot of different ways. It depends on the context, right? But one way to prove is just to show that it's, well, 1-to-1 and onto. How can you show this is 1-to-1? E to the x equal to e to the y implies what? X equals to y, therefore f is 1-to-1. Is it onto? Let y be an element of 0 to infinity, then f of the natural log of y is equal to e to the natural log of y is equal to y. Therefore, f is onto. There you go. That proves that f is a bijection. Consequently, isomorphism. The group of real numbers under addition is isomorphic to the group of real numbers, positive real numbers, under multiplication. Let's study the identity. What's the identity in G1 here in my example? What's the identity up here? It's just 0, right? Here, the identity what? And so I might call this EG1 for identity in G1. And down here, EG2 is what? What's the identity in G2 with respect to multiplication? What's that? 1, thank you. Don't worry me. So what happens when we take f of EG1, we get what? F of 0, which is e to the 0, which is 1, which, by the way, is EG2. Apparently, isomorphisms map the identity in the group to the identity in the target group, right? You could call G2 the target group if you want a term for it. What else? How about, what if we look at, what's f of minus x equal to? E to the minus x. What is e to the minus x equal to? It's equal to 1 over e to the x, aka e to the x to the minus 1, if you like that notation better. So I would point out to you that this isomorphism also maps the inverse element in the domain to the corresponding inverse in the target. It's changed an additive inverse into a multiplicative inverse because that's the nature of this isomorphism. Now these things I just pointed out, they're not just accidents of this example. These are general theorem, general results for an isomorphism. So let's state that theorem and prove it. I don't think we actually need that example anymore, so I'm going to get rid of it. So I called this proposition 2.3.4. And it says the following. If phi goes from a group G to a group H is an isomorphism of groups, of course, all right, then for each G and G, we have few things. In fact, this for each G and G really only refers to parts 2 and 3. It's got nothing to do with part 1, so it's just my weird way of stating it. I mean, I forget. There was some typesetting reason I did this. But anyway, e.g., equals to EH. The identity in G maps to the identity in H. That's one thing that's true. 2, the image of the inverse is the inverse of the image. The language I just used, if you're not familiar with it already, phi of G is the image of G under phi. In case you don't know what I'm talking about, that is what that term means. But that is obviously a complete and total digression from the proposition. So probably, I don't know, write that where you want or don't write it at all. It's up to you. And then 3 is that phi of G to the n is equal to phi of G to the n. Curses on you, English. All right. And that's for all n in the integers. So these are wonderful, wonderful properties of isomorphisms. Let's prove them. So I'm getting ready to erase. I mean, one of our larger programs in here, one of our larger projects, as we go on and find new examples and study new things, is to study how these new things transfer or don't transfer under isomorphism. Well, they always will transfer under isomorphism, actually. But you know, one of the questions that we'll be asking as we go forward is, you know, when are two groups isomorphic? You know, how do you decide that question? And we spend a lot of energy and time on that in here. So we're just getting started right now, but these are the fundamental things that we need for an isomorphism, all right? The identity has to map to the identity. Let's look at the proof of that. So how are we going to prove that? How about this? Phi of EG is equal to phi of EG, right? Because the identity is, E is equal to E times E, right? That's part of what it means to be the identity in the group. But then this is equal to what? By the structure preserving property of the isomorphism, we can say phi of the product is the product of the phis, right? And then what do we got? I'll write it. I'm going to write this on the second line again here just to emphasize something. Thus, by cancellation, law, phi of EG equals to what? Oh, I'm sorry. I guess to make it cancellation law directly, what should I have done? I should have said phi of EG times what? If I'm going to say cancellation law, I got to have something to cancel, right? What am I going to cancel? I'm going to cancel this and this. What do I write here to maintain equality? EH. Very good. And that's okay because EH times anything in H is just that anything again, right? It's the identity in H. So by cancellation law, phi of EG, well, just to make it more clear, EH equal to phi G. All right. So that proves part 1. Hey, question. This is a good time for us to interject a comment here before we go on to 2. Did I use injectivity here? Did I even use onto? Did I use one-to-one or onto here? I don't think I did. Right? I mean, I've used that phi of G is mapping into H. In other words, that phi is at least to function as it's presented. But I did not use injectivity. I did not use surjectivity. In fact, this would still be true if we did not assume that phi was an injection or a surjection. Those kinds of maps also have a name. If you just have a function from G1 to G2 like this, right, but we drop the condition of bijection, then it's said to be a homomorphism. So that already proves that if we have a homomorphism of groups, it preserves the identity. Right. So still true for homomorphisms. Let me say EG maps to EH under homomorphism. Exciting. Did I tell you guys about my new notification sound? No, it wasn't that exciting. It's just the math secretary telling me that she's printed things for me, which I'm appreciative of. But it's a little bit beside the point for us in here, huh? All right. So that finishes 1. Now let's move on to 2. All right, so how are we going to do this? Any ideas? What makes G inverse G inverse? How are we going to learn things about it? How about this? G times G inverse is equal to what? Yeah, I guess EG is at the moment, but E1 would have been a reasonable thing if I had numbered EG1 and G2. Anyway, EG, right? So then, what is phi? Phi of G inverse is equal to phi of EG. So that implies this, right? And then, thus, by 1 and definition of isomorphism, right? In particular, I'm using the structure preserving part. I'm going to say phi of G times G inverse is phi of G times phi of G inverse. And that's equal to, what's this? Phi of EG is what? It's EH, right? What did we prove last time? Or the time before? At some point, we have proved that the inverse, or you should have read, that the inverse, I forget. Let me stop digressing myself. So this shows already that phi of G inverse is the inverse of phi of G, right? Because it satisfies the needed equation, right? By the way, likewise, you can see easily that you can also have this, right? So by definition of the inverse, phi of G inverse is phi of G inverse. I'm sorry, I need to write it down. Stupid English. Phi of G, parentheses, inverse, is equal to phi of G inverse. By the way, did we need to use onto or one-to-one there? I don't think so, right? So again, this would also be true for a homomorphism. And finally, last but not least, part 3. Let's work on part 3. Here we're going to have to break into cases a little bit. Notice n equals to 0 is true since g to the 0 by definition is e sub g, and phi of g to the 0 is by definition e sub h. So phi of g to the 0 is equal to phi of g to 0 by 1. Right? Because part 1 we proved that the identity maps to the identity. So, let me decode this. This is nothing more than phi of EG is equal to EH, which we know that's 1. Yeah. So let's suppose n is positive. Also, well, one other comment. Also, n equals to 1 is true. Why? Because phi of g to the 1 is equal to phi of g to to the 1. I mean, yay, notation. There's nothing to prove there. That's just our definition of the first power, right? Not to be confused with the first order. Let's see here. Sorry. I know we're all still recovering from that movie. So, phi of gn. So I think we need induction here if I can. You know what I should do? I should stop working here and start working there so I don't go crazy. So suppose that phi of g to the n is equal to phi of g parentheses to the n for some n in the natural numbers, right? Consider phi of g to the n plus 1. What's that equal to? By definition, that is phi of g to the n times g. Right? That's our definition of g to the n plus 1. We defined it recursively. Then what? Well, this is phi of g to the n times phi of g. Why can I do that? What's that? That's the structure preserving property of the isomorphism, right? That multiplication transfers from the domain to the target, to the range. All right, and then what? Oh, by the induction hypothesis, that's phi of g to the n times phi of g. That's by our induction hypothesis. This is because the isomorphism, and this was definition of what? G to the n plus 1. So to be sure you're not losing points in proofs, we should explain ourselves, right? Sometimes I say things in words in here and I don't write them on the board. Things I say in words and don't write on the board still matter. Right. I do post solutions to tests and stuff, so you get to see there, you know, what a needlessly verbose solution looks like. Anyway, and then what? This is equal to phi of g to the n plus 1, what? By definition of, you know, n plus first power. Right, by definition of the power again. And what have we shown? We've shown that the claim of 3 is true for n plus 1 if it's true for n. So by proof by mathematical induction, it follows that 3 is true for all positive integers. Therefore, by PMI, phi of g to the n is equal to phi of g to the n for all n in the natural numbers. We're still not done. What's left? Yes, negative numbers. So what can we do there? Let's suppose, continuing our proof, if n is less than 0, then there exists m in the natural numbers such that what? M as in mommy, n as in nanu nanu. So n is equal to minus m. And then we can study the following, right? So phi of g to the n is what? It is phi of g to the minus m by construction of m, right? And then this is equal to phi of g inverse to the m. So this is by a law of exponents. Actually, that's not by the law of exponents. That's the definition of negative powers. we defined negative powers of a group element to be the corresponding same number of powers for the inverse of the group element. That's how we defined such a power. Now, is G inverse in the group? Yes. Did the thing we do over here, is this true? I mean, to be more clear here, this is true for all G and G, right? Right, that we have proved for arbitrary G. So in particular, we can apply what we've already done to the case of G inverse, which means that I'm allowed to pull the M out using what I've already proved for part 3. By proof of 3 for the natural number part, yeah? Or if you like, you could have given this thing a name. You could have called this thing ghost. Here I'm trying to make my ghost higher definition. There we go. AKA ghost. There we go. And then finally, what is this? Well, by part 2, we know this is also phi of G inverse. I need some more parentheses, right? Phi of G inverse to the M, which is, by definition, phi of G, parentheses, to the minus M, which is phi of G, parentheses, to the N. So there you go. Now we have proved this identity for negative powers, positive powers, 0 powers, all your powers. Right? So 3 is true. Hooray! Next up. Oh, by the way, still true for a homomorphism. All right. Theorem. Actually, I'm not sure it's a theorem. I may have labeled it something else. Oh, it is a theorem. Hooray. By the way, the significance and/or difference between theorems and proposition in my notes is questionable at best. I do not use these terms in an educated way. I just use them in a haphazard way. All right. I do tend to make corollaries related to a theorem or proposition. That much is true. But beyond that, what's the difference between theorem, proposition? For me, debatable. Now, a case can be made for using those terms in a systematic and proper way, but the case has never been made to me in a forceful enough way that I do it. Okay, so that doesn't mean that you shouldn't do it. It just means that, I'm not perfect. All right. You're like, oh, that's news. Phi from G to H is an isomorphism. That's being sarcastic. Isomorphism. Oh, wait a minute. I don't have to tell you guys that. This is not the class I have to explain when I'm being sarcastic. If phi goes from G to H is isomorphism, then, now this is where it would not be true for a homomorphism. If we drop the bijectivity, it's no longer true here. Okay. For all A and G. And there, the bars mean order. All right. So here's the proof. First of all, what if we have the identity? If A is equal to E, then phi of E is equal to, well, phi of E is equal to E. Fine, you have been using EG and EH up to this point. Fair enough, I just dropped the, I hope you can forgive me for using E for both, all right? So what's that say? That says that the order of phi E is equal to, well, 1, and the order of E is equal to 1, so the claim of it's true. They both have order 1. All right. So let's suppose that A is not equal to E, and let's suppose that the order of A is equal to n. What's that mean to say that the order of A is equal to n? That means that A to the n is equal to E, and n is what? Smallest power such that this happens. Now, I can be more precise than that, right? In other words, there does not exist a j less than n such that what? Such that A to the j is equal to E. I should clarify, of course, 0 less than j. Minus n will give you E. All right. So check it out. Notice that phi of A to the n is equal to what? Phi of A to the n, right? By what we just worked through. And what is A to the n? It's the identity. And what's phi of the identity? It's the identity. So what's this tell us? This tells us that the order of phi of A is at most n. This is a mistake you guys make a lot when I ask a question about order. You'll show me that the order could be n, but then you won't finish the thought and prove that there doesn't exist any smaller power which also could be E. Right? So that we're not done. We've just shown it's at most n at this point. Now then, what do you do? How about this? If 0 less than j less than n, then phi of A, so the same calculation pretty much, right? Phi A to the j is equal to phi of A to the phi of A to the j, right? Now, towards a contradiction, suppose that was E. Towards a contradiction, suppose it was E. I'll put that in red. Contradiction. Oops, I've got my addition and multiplication mixed up. What should I write there? E, right? I should identity, not 0. I'm an idiot. What is E equal to? Part 1, proposition. Phi of E, right? Phi is a bijection, which means it's 1 to 1. What does that say about A to the power j? A to the power j equals to E. Oops. That's a contradiction to A having order n. Therefore, what I wrote in red is absurd, and in fact, no power of j less than n gives us back the identity, which proves, right? So this implies, continuing the red thought, that the order of phi of A is equal to n. Does this complete the proof? Seems like it. Does it, though? Yes. Oh, no. That was not a... Okay. What's the other possibility? When we write that the orders are equal, this allows also the possibility that A could have infinite order. So you could have that the order of A is infinity, which means that no power of A ever gets back to the identity. And through very similar calculations, you can prove that if the order of A is infinite, the order of phi of A must also be infinite. The argument's in the notes, I just don't want to write it out right now. Okay? So this is not, it's almost done, but we also have to address the infinite order case. All right, so notice that a corollary to this, now this is not true for homomorphisms. For homomorphism, we don't have this injectivity, right? So we wouldn't get quite the same result. For homomorphism doesn't have to preserve the order of elements. Something else happens. We'll talk about it later. All right? Now, but there is something neat that we can say from all this, which is that if we have an isomorphism of groups, it preserves the order. So we've just proved it preserves the order of elements. But if you think about it, what's that say? That says that two groups, what's a corollary to this? Two groups are isomorphic if what? Corollary. If G1 is isomorphic to G2, then the cardinality of G1 must be equal to the cardinality of G2. They must have the same size. And what else? They must have the same number of elements with matching orders. All right? Let me show you what I mean by that. So we have Z4 under addition, right? 0, 1, 2, 3, 0, 1, 2, 3, right? You can easily fill out this Cayley table, right? We can also look at U8. What is U8 got? It's got your 1, it's got your 3, you got your 5, you got your 7. 1, 3, 5, 7. My apologies if I'm doing a homework problem for you. You'll forgive me if that happened, I'm sure. Probably is not. But this one's easy enough to fill out, right? 0, 1, 2, 3, 1, 2, 3, 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 1 is 0, 1 plus 2 is 3, 3 plus 2, 3 plus 2 is 0. I mean, it's symmetric if you do it right, so 3 plus 3 is 6, which is 2, 1, 0. If I did it right, each row and column, ignoring the label ones, should just have one copy of each group element, right? So, okay. How about this? 1, 3, 5, 7, 3, 5, 7. 3 times 3 is 9, which is 1. 3 times 5 is 15, which is 7. 3 times 7 is 21, which is 5. 5 times 3 is 15, which is 7. 5 times 5 is 25, which is 1. 7 times 7 is 49, which is 1. 5 times 7 is 35, which is 3. 7 times 3 is 21, which is 5. 7 times 5 is 35, which is 3. Yeah. All right. There you go. That's a complete description of the structure of Z4 additively and U8 multiplicatively. So these are two groups. They have the same order. They're both order 4. So maybe they're isomorphic. Verdict's not out yet, right? Check out the orders of the elements. What are the orders of the elements here? What's the order of 0? It's 1. It's the identity, right? What's the order of 1? The order of 1 is also equal to the order of 3. And those both have order 4. because you have to do 1 plus 1 plus 1 plus 1 in order to get back to 0. Right? 3. 3 plus 3 is 6, plus 3 is 9, plus 3 is 12. Only after you add it to itself 4 times do you get back to 0. The order of 3 is 4 in Z4. But 2, the order of 2 is 2, because 2 plus 2 is 4. So this group has one element of order 1, 2 elements of order 4, and 1 element of order 3. Excuse me, 2. How about this one? In U8, the order of 1 is 1, but the order of 3 is equal to the order of 5, is equal to the order of 7, is equal to 2. Because those are all their own inverses, just like that matrix we saw last time. When an element is its own inverse, it has order 2. It satisfies a squared equal to the identity. So these groups are not isomorphic by that theorem. Corollary, if you like. All right. So there's another one I wanted to show you. I'm gonna put it up on the big screen here. What is it?
So you could also technically figure that out just by comparing each square.
You could have.
Seeing that the same number can map to two different.
Just start again.
So you said that, if those two, we know that those two were not isomorphic based on what we just did there.
Right. If we can show that.
You could also do that just by comparing them the way that we did those other two.
Oh, that is true. They don't have the same pattern, so they're not isomorphic. Yeah.
Because
But we really like to use what I just said more as a method because. Whoa. Sorry. Uh-oh. Don't look at this. No. Ah. Huh. I guess I should actually close Windows before I open it up. Yeah. Fortunately, I'm glad that sometimes I open one of these things up, then I'm obligated to edit. This is not one of those cases, so I'm happy. I put all the course IDs for, which was that? Was it differential equations? I think I put up the roster with the course IDs. It's like, ah! So I had to edit that. So annoying. We are almost done. I really don't have much more to show you. So something I wanted to mention to you that's fun. So these are just a couple of, well, first of all, a couple of fun examples. So what is Z4 isomorphic to? I just showed you what it's not isomorphic to. Z4 is not isomorphic to U8. What is it isomorphic to? Well, you could look at the set of complex numbers, 1, I, minus 1, and minus I, right? If you look at those, they're closed under inverses. They actually form a little group of complex numbers. Plus or minus 1 and plus or minus I. Those 4 complex numbers together form a group with respect to complex multiplication. And in fact, you can prove that this isomorphism, psi of I to the k, which is k mod 4, that actually defines an isomorphism. So there's an isomorphism between Z4 and the 4th roots of unity in the complex numbers. What are the nth roots of unity? Well, the nth roots of unity are, they are of the form e to the 2 pi I over n. And if you look at e to the 2 pi I over n, so you have to remember e to the I theta is cosine theta plus I sine theta. And we have this theorem, the Moivre's theorem. That's not how to say it, but anyway. And anyway, long story short, if you take the principal nth root of unity and you raise it to the n power, you get back cosine 2 pi plus I sine 2 pi, which is 1. So this shows you that any power of e to the 2 pi I over n, when you power it to the nth power, it gives you back 1. So it's a solution of z to the n equals to 1. And we call such solutions nth roots of unity. This little argument right here, the omega sub n to the k power, well, that's equal to cosine 2 pi k over n plus I times the sine of 2 pi k over n. And I just point out that that's not equal to 1 for 0 less than k less than n. Therefore, well, anyway. This was not my larger point here. Well, anyway, we'll talk more about that another day, but what I wanted to say to end, I'm not done yet. I'm not done yet. Hands away from that. So, one of the big ideas, guys, is the composition of isomorphisms is an isomorphism. So like if I have an isomorphism from G1 to G2 and I've got another isomorphism from G2 to G3, then G1 and G3 are isomorphic. Is any group isomorphic to itself? The answer is yes. You can just look at the identity mapping from the group to itself. That's an isomorphism. So isomorphism is reflexive. By the way, if psi is an isomorphism, then psi inverse is also an isomorphism. So it's symmetric. If G1 is isomorphic to G2, then G2 is isomorphic to G1. And you also have transitivity. So isomorphism on the set of all possible groups, isomorphism is an equivalence relation. All right? So that's I think that's kind of interesting. Have I ever explained to you guys, that see, it's going back to my email. Have I ever, guys, explained to you that I'm Batman? So let me explain to you why I'm Batman, and then we'll have a nice weekend. All right, here we go. Have we read? We've read it? Very good. So what I like to say is, up to a Wu-Tang name generating equivalence, I am Batman. Have a good weekend.